Hello everyone. This is the last session 4 of week 7 and we'll be discussing scaling Horovod and picking the right tool. After this, we do have session 5 wherein we will be doing the hands-on of this week, which will be on distributed training on a DGX server. So from the theory point of view, this is the last session of the contents which I will be covering. So when we talk about distributed training, we actually come up at two questions basically on terms of how the scaling will behave. One is called as the strong scaling and another one is called as weak scaling. So the strong scaling basically is there's a fixed problem and we go on increasing the number of GPUs. So effectively, if you relate it to the Amdahl's law, it basically takes a situation wherein the number of processors become infinite, right? So the serial portion stays and the parallel portion actually completes in 0 units of time, right? So this basically means, does my existing job finish faster with 8 GPUs instead of 2? So ideally the time is equal to 1 by n, and reality is it runs into communication flows or communication problem, right? So we should also understand that there is a point of saturation of the throughput actually because of the communications getting increased when we increase the number of GPUs, right? And weak scaling basically talks of fixed per GPU work and more GPUs. So this basically questions the thing that if I scale to a bigger problem, does my wall time stay constant? So ideally the time is constant, but reality again the communication adds the overhead. So this matters when you are trying to do a pre-training basically a larger model using more data in fixed wall time. So the basic idea here is the most real AI workloads are weak scaling. We want basically to train bigger things with our extra compute, not just finish the same job faster. So this is one of the important things which we are talking about. We should concentrate more on how weak scaling actually improves, okay, and we use them for the AI workloads, right? Where does the missing efficiency go? That basically means if we have the useful compute and the time is spent basically on the compute part of it, the 64% is spent on compute, then all reduce, right? When you're talking of larger models, smaller buckets, bigger grad accumulation, 12% is spent on that. Slow GPUs are basically when you talk about pinning the GPUs and then there are homogeneous nodes, 10%. Load imbalance gives us about 6% of time being utilized. Host overhead 4%, data loading stalls 4%. So the basic idea here is that when we want to measure our efficiency of how much we use our GPUs for compute and where all the other bottlenecks are, okay, so the hotspots basically, so as to say, the PyTorch profiler plus Torch Cura event gives us the actual breakdown, right? And we can basically use certain profilers for profiling and seeing what basically happens, okay? So basically, when you talk about the optimization levers or the way in which optimization can be achieved in case of distributed training, we are talking of mixed precision things, right? And floating point 16, BF16, halves memory and bandwidth, and larger per GPU batch plus gradient accumulation, and then we can tune the NCCL bucket size and count. Basically it defaults to 25 MB. So larger model benefits from larger bucket size, small models for more smaller buckets. So these are all basically trying to set in our own parameters, right? and then you have this gradient compression, then all reduce again we saw. Okay, and the next batch communication, which is basically trying to improve the ddp's backward, right, data collection as a hook. So these are certain things which we are generally using in case of optimizing the various distributed training parameters, right? And so let us try to understand the Horovod thing which we thought. So we saw DDP. We also know FSDP to some extent. We have not worked on the zero thing, neither FSDP, but we will work in the next session using DDP and to some extent certain other things like deep speed. But Horovod is something which is very less memory efficient from that point of view. The complexity wise, it's medium complex and it's comparable to DDP, and the framework is supported by PyTorch, TF, MXNet. Okay, so DDP is only supported by PyTorch. FSDP also is a thing which actually PyTorch started, and Deep Speed Zero also is supported by PyTorch. So one of the things which people have started using is DDP and FSDP. Okay, from the PyTorch perspective, and basically Horovod was initially very good. In the last run of our course, we actually did Horovod, but now the DDP and FSDP is more prevalent and more useful. So this time we have covered DDP and FSDP actually. So if you see the DDP, memory efficiency, full replica is low, but setup complexity is also very low. Speed wise, it's fastest. From a FSDP point of view, memory efficiency is very high, setup complexity is medium, and you can get the near DDP with overlap, right? And deep speed zero is highest. You can offload certain things to CPU. Complexity wise, medium high. You can compare it to FSDP, and basically you have to use certain plugins. Okay, so this is how basically a quick comparison of all of these distributed training approaches basically. So just to have an academic thing is that Horovod is MPI based alternative, and it was actually Uber's distributed training library. Okay, it uses MPI and it does not use C10D for rendezvous and NCCL for collectives. So it is framework agnostic. That means you can use TF, PyTorch, MXNet. The launcher is Horovod run. Okay, and it basically uses MPI run. Basically, it wraps the MPI run stuff, and the activity has declined since PyTorch added first class DDP. So that is the reason why we are shifting to DDP and PyTorch, right? So, but almost the same thing. What Horovod does, actually DDP does very easily, and it's very simple as well because PyTorch actually does a lot of things in builds, right? So the way in which Horovod does things is a bit similar to what DDP does, but yeah. So if you see, like, if the decision has to be done for choosing a framework and what is the right tool if you need to choose. So S7B model, 8 to 32 GPUs, fits in the GPU memory. We go in for DDP. It's simplest, what 90% of the teams generally use. And then if it's 13 to 70 billion parameters, memory tight but pre-layer fits, it is FSDP, shards weight plus grads plus optimizer state and all of that. And it keeps the DDP simple, right? Very tight memory situation, you want the library level optimization, we go in for deep speed, right? And then existing TF MXNet code bases, HPC clusters, people still use Horovod a bit, okay, because it uses MPI plus RAM and so on and so forth. And if there is a situation wherein one single layer doesn't fit on a GPU, we go in for tensor parallel. And if there are trillion parameter frontier models, we go for 3D parallel. That basically means we combine the data plus the tensor plus the pipeline. Okay. So basically, what happens? We basically, undoubtedly, nowadays we should use DDP. And when we actually encounter something like out of memory issues, right, we go in for FSDP, is what actually is the general parameter to judge actually what needs to be used, either DDP or FSDP, right? So the scaling efficiency, we will discuss this in our the next session when I execute the programs, right, and see actually how basically the throughput and the efficiency changes. Okay, so from the distributed training point of view, we started with four parallelism axis. We talked about data tensor pipeline, sharded concepts, and how do you actually write a TTP script, right? In a sense that we have not written it, but we know that we have to use sampler, we have to use a concept of distributing it, then collecting it back. Okay, so gather, reduce, all of that we have seen. Then we know how do we use the debugging thing using NCCL, and then scaling, and then whether we should use DDP or FSDP or deep speed versus Horovod versus sensor pipeline. A brief idea about all of this, not of course in detail. So in the next session, we will try to basically see, okay, the hands-on, and the following week 8 we'll try to see how scalable training dynamics and deployment engineering to some extent, okay, is covered, wherein we should understand as to once we have trained our model at scale, the next week will teach us how to ship those models, okay, which have survived the training. So thank you, and let's go on and see the hands-on for this week.